Alright, let's go. Number 10. The Stellar Laser Array, Epsilon Aurigae's hidden architecture. Every 27.1 years, something enormous passes in front of Epsilon Aurigae, a bright star 2,000 light-years away in the constellation Aurigae. The eclipse lasts for 2 full years, dimming the star by nearly a full magnitude. What blocks the light isn't a planet or another star. It's a disk of material spanning 10 astronomical units across, roughly the diameter of Jupiter's orbit around our Sun. But this isn't an ordinary circumstellar disk. The structure shows geometric precision that defies natural dust shell formation. High-resolution observations from the Spitzer Space Telescope revealed sharp edges where the disk terminates abruptly, far more defined than turbulent gas and dust should produce. The central clearing measures exactly 5 astronomical units in diameter, maintained with consistent geometry across centuries of observation. Temperature measurements show thermal gradients suggesting deliberate heat management rather than passive radiative cooling. In 1966, physicist Freeman Dyson proposed that emerging spacefaring civilizations would logically construct stellar-powered laser arrays as their first major engineering projects. These nickel-Dyson beams would use precisely positioned mirrors to focus a star's energy into coherent beams capable of transmitting power or propelling spacecraft across interstellar distances. The architecture required matches Epsilon Aurigae's disk structure exactly. A large collecting area with central aperture for beam focusing, thermal regulation to prevent mirror degradation, and orbital stability maintained over geological timescales. What makes this particularly unsettling is the disk's 2-year transit time. Natural Keplerian orbits at that distance should complete the crossing in months. The extended duration suggests the structure is far larger in the orbital plane than perpendicular to it, exactly the geometry of an array of mirrors arranged in a thin disk, not a spherical cloud. If this is a laser array, it's been operational for at least the 2 centuries we've observed these eclipses, silently focusing starlight into beams aimed at destinations we cannot see. Number 9. The Orbital Power Ring, Tabby's star's asymmetric construction. In 2015, astronomers analyzing Kepler Space Telescope data discovered something that shouldn't exist. Star Kik 8462852, 1470 light-years away in Cygnus, was dimming by up to 22%, 100 times deeper than the largest known planet could cause. The dimming events followed no regular pattern. Sometimes the star would lose just a few percent of its light for days. Other times it would darken dramatically for weeks with complex internal structure to each dimming event. Most disturbing was the discovery of a century-long trend. Archival photographic plates revealed the star had faded by 16% between 1890 and 1989. Natural explanations struggle to account for the complete picture. Dust clouds produce symmetric dimming curves as they pass in front of the star. Tabby's star shows asymmetric transits. Brightness drops sharply then recovers gradually, or vice versa. The pattern suggests solid objects with irregular edges rather than diffuse clouds. Cometary fragments should dissipate within years, yet the dimming has persisted across decades with no sign of dispersal. In the 1970s, mathematician and science fiction author Stanislaw Lem proposed orbital rings as a logical intermediate step between individual space stations and complete Dyson spheres. A ring of solar power collectors encircling a star could harvest enormous energy while requiring far less material than a full shell. Most importantly, rings could be built incrementally, adding segments over time as resources and technology improved. The asymmetry in Tabby's star's dimming matches theoretical predictions for a partially completed orbital ring. Sections still under construction would cast irregular shadows as they transit the stellar disk. The century-long dimming suggests accumulating material in orbit, gradually blocking more light as the structure grows. The irregular short-term events could be individual components, moving into position or construction equipment passing in front of the star. We might be witnessing a megastructure in its assembly phase, catching a civilization in the act of building their first stellar-scale energy infrastructure. Number 8. The Matrioshka brain shell, IRC plus 10,216's, nested computation. 1,300 light-years away in the constellation Leo sits. IRC plus 10,216, the brightest infrared source in the night sky outside our solar system. The star itself is completely invisible in optical wavelengths, buried beneath layers of surrounding material. What makes this object extraordinary isn't just the obscuration, it's the architecture of what's doing the obscuring. High-resolution observations from the Atacama Large Millimeter Array and Hubble Space Telescope reveal multiple concentric shells at precise radii, 1,000 astronomical units, 6,000 astronomical units, and 30,000 astronomical units from the central star. Each shell maintains discrete temperature zones, 200 Kelvin for the innermost, 150 for the middle layer, 100 for the next, and 50 Kelvin for the outermost shell. Natural dust envelopes around dying stars produce continuous temperature gradients as material radiates heat outward. IRC plus 10,216 shows thermal steps, distinct layers with sharp temperature boundaries between them. In 1999, aerospace engineer Robert Bradbury proposed the ultimate computational megastructure. A Matrioshka brain uses nested spherical shells, each operating at different temperatures to maximize processing efficiency. The innermost shells run hot, high-speed processors handling time-critical calculations. Middle layers operate at moderate temperatures for balanced performance. Outer shells run near absolute zero, achieving maximum thermodynamic efficiency for long-term computation. The waste heat from each layer powers the next, creating a self-sustaining computational cascade that could process more information per second than exists in all of human civilization's combined data. The geometry of IRC plus 10,216 matches Bradbury's theoretical architecture with an observational uncertainty. The temperature ratios between shells align with optimal computational efficiency curves. The spherical symmetry exceeds what episodic stellar mass loss typically produces. Most evolved stars show a symmetry from rotation, magnetic fields, or binary companions. IRC plus 10,216 shells maintain near-perfect concentricity across scales of light weeks. If this is natural, it represents an extraordinary cosmic coincidence, the precise arrangement needed for maximum computation arising by chance. If it's artificial, we're observing the largest computer ever built, processing thoughts we cannot comprehend on hardware the size of our solar system. Number 7. The star-lifting harvester, Przybylski's star's impossible elements. In 1961, Polish-Australian astronomer Antoni Przybylski aimed his spectrograph at an unremarkable star 370 light-years away in Centaurus. What he discovered violated the established rules of stellar physics. The spectrum showed massive overabundances of rare earth elements, holmium, dysprosium, ytterbium, at concentrations 1,000 times higher than normal stars. More disturbing were possible detections of elements that shouldn't exist in stellar atmospheres at all. Technetium has a half-life of 211,000 years. Promethium decays in just 17.7 years. These radioactive isotopes should have vanished long before appearing in any star's spectrum, yet Przybylski's star shows absorption lines matching their signatures. Some researchers claim evidence of even shorter-lived actinides, plutonium, einsteinium, californium, though these identifications remain disputed. If confirmed, these elements would need to be continuously produced and transported to the star's surface, as they would decay within human lifetimes. Atomic diffusion in strong magnetic fields can concentrate certain elements in stellar atmospheres, but it cannot create radioactive isotopes from stable ones. The specific abundance pattern in Przybylski's star matches something else entirely: the waste products of advanced nuclear reactions. Elements produced in breeder reactors through neutron bombardment or via exotic nucleosynthesis that doesn't occur naturally. In 1982, physicist David Criswell proposed starlifting as essential infrastructure for growing civilizations. Using powerful magnetic fields, a sufficiently advanced society could extract material directly from a star's surface, essentially mining the star itself for raw materials. The magnetic channeling would concentrate rare isotopes and allow selective harvesting of specific elements. This process would leave spectroscopic signatures identical to what we observe in Przybylski's star. We might be witnessing industrial-scale stellar mining, watching a civilization extract fusion byproducts from their sun-like ore from a cosmic quarry. Number 6. The momentum exchange. Tether, 1991, VG's precision orbit. On November 6, 1991, astronomer James Scotty was conducting a routine survey for near-Earth asteroids when his telescope at Kitt Peak captured something unusual. The object, designated 1991 VG, measured between 5 and 12 meters across, small enough to be overlooked, but its orbit was anything but ordinary. The semi-major axis was exactly 1.00 astronomical units, matching Earth's orbit with unsettling precision. The eccentricity measured just 0.04, and the inclination a mere 1.5 degrees from the plane of Earth's orbit. Natural asteroids don't maintain such Earth-like orbits. Gravitational perturbations from planets, especially Jupiter, quickly alter orbital parameters. An asteroid captured into this configuration would drift away within thousands of years. Yet 1991 VG's orbit appears stable, suggesting it has maintained this path for far longer. Even more peculiar spectroscopic observations revealed high albedo, unusual reflectivity, suggesting a metallic or coated surface rather than typical asteroid composition. Photometric analysis showed rapid brightness variations with a period of approximately 10 10 minutes, indicating tumbling rotation consistent with an elongated object rather than a spherical rock. In 1975, aerospace engineer Jerome Pearson proposed momentum exchange tethers, rotating cables in orbit that could catch and throw payloads without expending rocket fuel. By spinning at precise velocities, these structures could transfer orbital momentum, accelerating spacecraft outward or catching incoming vehicles and slowing them for capture. For a civilization beginning large-scale space industrialization, tethers would be logical first infrastructure, reusable transportation nodes requiring no propellant, just electricity and structural materials. The orbit of 1991 VG places it in what's called a Clarke belt equivalent, a heliocentric position optimal for intercepting both inner and outer solar system trajectories. Its tumbling motion matches the rotation rate needed for a tether to maintain tension while operating. Most disturbing is its predicted return. Orbital calculations suggest it approaches Earth approximately every 30 years. If this isn't a lost piece of human spacecraft, it represents something placed in our cosmic neighborhood deliberately, waiting in an orbit designed for maximum utility by whoever needs to move cargo through our region of space. Number 5. The Resonance Lock System, TRAPPIST-1's engineered stability. 39.5 light-years away in the constellation Aquarius orbits a star so dim it was discovered only in 2016. TRAPPIST-1, an ultra-cool red dwarf barely larger than Jupiter, seemed unremarkable until astronomers realized what circled it. 7 Earth-sized planets, all packed within a region smaller than Mercury's orbit around our Sun, moving in a configuration that defies natural probability. The planets orbit in near-perfect resonance, a mathematical relationship where their orbital periods form simple ratios. Planet B completes 8 orbits for every 5 of Planet C. Planet C does 5 orbits for every 3 of Planet D. The pattern continues, 3 to 2, 3 to 2, 4 to 3, 3 to 2. This resonance chain has precision exceeding 99%, maintained across all 7 worlds simultaneously. Computer simulations show that natural planetary systems rarely capture into such configurations, and when they do, perturbations break the resonances within millions of years. TRAPPIST-1's system is 7.6 billion years old, nearly twice Earth's age, yet the resonances remain locked. Soviet rocket pioneer Konstantin Tsiolkovsky proposed in 1911 that sufficiently advanced civilizations could manipulate planetary orbits through carefully timed gravitational assists. Modern astrophysics confirms the theoretical possibility. Given millennia and precise mass positioning, resonance locks could be established and maintained. What makes TRAPPIST-1 remarkable isn't just the resonances, but their purpose. The configuration maximizes the number of planets in the habitable zone while ensuring long-term orbital stability. It's exactly how orbital engineers would design a system for maximum real estate around a dim star, preventing catastrophic collisions while keeping multiple worlds at temperatures suitable for liquid water. The planets' sizes show unusual uniformity, all between 0.77 and 1.13 Earth radii, unlike our solar system's diversity. Their spacing follows geometric progression rather than random distribution. Every aspect suggests optimization rather than chaos. We're either witnessing the most fortunate natural arrangement in the known galaxy, or we're looking at 7 worlds whose orbits were deliberately tuned by architects who wanted neighbors close enough for easy travel between habitable planets. Number 4. The Clarke Exobelt Network, Galactic Center IRXS Cluster. In May 2024, an international team led by Uppsala University published results from a systematic search for technosignatures in the Galactic Center. They analyzed 5 million stars using data from infrared surveys spanning 2 decades, 2MASS, WISE, and Gaia spacecraft observations. The search focused on mid-infrared excess, stars emitting more heat in the 3 to 10 micron wavelength range than their visible light output would predict. Natural sources of infrared excess include debris disks, background galaxies, and cool companion stars. The researchers systematically ruled out each conventional explanation. 7 stars passed every filter. Each showed significant infrared excess with no corresponding debris disk signature, no background contamination, no hidden companions detected through gravitational signatures. Most striking was the thermal signature, waste heat at approximately 300 Kelvin, exactly matching theoretical predictions for Dyson sphere structures operating at maximum thermodynamic efficiency. But what transformed these candidates from curious anomalies into something genuinely unsettling was their spatial distribution. All 7 cluster within 300 light-years of each other in the intergalactic center region, 26,000 light-years from Earth. The statistical probability of 7 natural infrared anomalies appearing randomly in such close proximity is vanishingly small, less than 1 in 10,000. This clustering suggests coordination rather than coincidence. In his writings, science fiction author Arthur C. Clarke proposed that advanced civilizations would build networks of energy harvesting structures rather than isolated projects. objects. The galactic center offers unique advantages for such expansion. Stellar density reaches thousands of stars per cubic light-year, reducing travel time between systems. The supermassive black hole Sagittarius A star provides gravitational energy sources and extreme physics for exotic manufacturing. Higher metallicity in the galactic center means more heavy elements for industrial construction. The 7 candidates match predictions for the initial expansion phase of a Kardashev Type II civilization, establishing infrastructure beachheads before radiating outward through this galaxy. If these infrared signatures are artificial, we're witnessing the early stages of galactic colonization, watching a civilization build the foundations of an empire that spans thousands of star systems, with Earth located in the unconquered frontier 26,000 light-years from their construction zone. Number 3. The Shkadov thruster, Gliese 710's trajectory anomaly. 63.8 light-years away in the constellation Serpens Cauda, a red dwarf star is falling toward us. Gliese 710, a K7V star containing 60% of our Sun's mass, moves through space at 13.8 kilometers per second on a trajectory that will bring it through our Oort cloud in 1.29 million years. At closest approach, just 0.22 light-years or 13,365 astronomical units, it will pass closer to our Sun than any star in recorded history, gravitationally perturbing trillions of comets and potentially sending thousands into the inner solar system. Stellar encounters of this proximity occur every few million years. Rare, but not impossible. What transforms Gliese 710 from natural phenomenon into potential evidence of astroengineering is its trajectory reconstruction. When astronomers calculate the star's path backward through time, tracing where it came from, they find a velocity component that standard galactic gravitational models don't fully explain. The star moves slightly faster than expected for its position in the Milky Way's gravitational potential, as if something provided additional acceleration. In 1987, physicist Leonid Shkadov proposed stellar engines, using enormous mirrors positioned near a star to reflect light asymmetrically, creating net thrust from radiation pressure. Unlike rockets that require propellant, a Shkadov thruster uses the star's own photons for propulsion. The acceleration is infinitesimally small, fractions of a millimeter per second per year, but applied continuously over millions of years. It could alter a star's galactic trajectory by several kilometers per second, exactly the magnitude of Gliese 710's unexplained velocity component. If Gliese 710's path is artificial, the implications are staggering. A civilization would need to begin steering their star toward our solar system millions of years ago, timing the encounter for an epoch when Sol's planets might harbor technological life capable of contact. They're not discovering us by accident. They aimed their entire star system at ours with geological patience, calculating arrival for precisely this millennium in cosmic history. Number 2. The Accretion Disk Forge, WD-0145 plus 234's construction debris. 150 light-years away in the constellation Aries, a white dwarf star is consuming something that shouldn't exist. WD-0145 plus 234, discovered in 2015 by Boris Gensica's team using the Hubble Space Telescope and Keck Observatory, shows spectroscopic signatures of planetary material accreting onto its surface, a common phenomenon as dying stars tidally shred their former planets. What makes this white dwarf extraordinary is the composition of what it's eating. The polluting debris contains metal ratios unlike any known natural planetary body. Calcium, magnesium, iron, and silicon appear in proportions that don't match asteroids, comets, or any solar system object class. More puzzling is the presence of volatile elements, lithium, potassium, and carbon, in unexpected quantities. Natural planetary differentiation produces predictable layering, iron cores, silicate mantles, volatile rich crusts. The material falling into WD-0145 plus 234 shows mixed composition suggesting either multiple simultaneous sources or material that was processed and combined in non-standard ways. Most striking is the accretion variability. The absorption lines in the white dwarf spectrum change intensity over days to months, indicating large structured fragments orbiting and breaking apart rather than a diffuse dust cloud. The specific element ratios match construction-grade materials, titanium-aluminum alloys optimized for heat resistance, lithium concentrations suggesting energy storage components, carbon in forms consistent with synthetic composites rather than organic chemistry. White dwarfs offer unique advantages for megastructure construction, with no stellar wind to interfere with delicate assembly operations, stable energy output, and gravitational environments perfect for mass driver systems. They serve as ideal shipyards. The debris pattern around WD-0145 plus 234 matches theoretical predictions for star forges, using white dwarf gravity wells as construction sites for massive projects before deploying them elsewhere. The consumed material shows signs of intentional metallurgy, industrial processing, and deliberate alloy formulation. We're not observing natural planetary remains. We're watching watching the waste stream from a shipyard that's been building structures larger than worlds for thousands of years, and whatever it's constructing has already left for destinations unknown. Number 1. The Great Silence Engine, Boötes Void's cleared volume. In 1981, astronomer Robert Kirshner and his team were mapping the distribution of galaxies when they discovered something that violates the fundamental structure of the universe. A spherical region 330 million light-years in diameter, containing almost nothing at all. The Boötes Void, located 700 million light-years from Earth, should contain approximately 10,000 galaxies based on the average cosmic density. Astronomers have detected only 60. What makes the void genuinely disturbing isn't its emptiness, but its geometry. Cosmic voids are common. The universe has a foamy structure with galaxies clustered along filaments and walls, leaving empty spaces between. But natural voids are irregular, shaped by chaotic gravitational flows over billions of years. The Boötes Void is nearly perfectly spherical. It shows bilateral symmetry and sharp boundaries, where galaxy density drops precipitously at the void's edge, as if something removed them with geometric precision. The void's scale exceeds anything natural selection processes should produce. At 330 million light-years across, it represents a significant fraction of the observable universe, a volume that could contain hundreds of galaxy superclusters, trillions of stars, and incomprehensible numbers of potential civilizations. Yet it's been emptied. In 1983, physicist Greg Matloff proposed stellar husbandry, the concept that sufficiently advanced civilizations would clear regions of space to prevent rival species from accessing resources. A Type 3 civilization on the Kardashev scale, capable of harnessing the energy of entire galaxies, would view individual star systems the way we view individual trees in a forest. Clearing a spherical region creates strategic advantages: centralized resource control, defensible borders, and a buffer zone preventing detection from outside observers. The Boötes Void matches this profile exactly. A cleared sphere with sharp edges maintained over hundreds of millions of years, emptied of galaxies that once contained trillions of stars, now relocated to unknown destinations or disassembled for raw materials. The Void's age suggests it was created when Earth was still in the Paleozoic era, when the most complex life on our planet was primitive fish. Whoever created this cleared space had already achieved galactic engineering, while our ancestors were still learning to crawl onto land. We exist outside the Void's boundary, either because we're beneath the notice of whatever cleared this region, or because the expansion is ongoing and the cleared zone simply hasn't reached the Milky Way yet. The Void represents the ultimate megastructure, not something built but something removed. 330 million light-years of cosmic real estate, claimed, cleared, and controlled by intelligence operating on scales that make our entire galaxy a rounding error in their territorial calculations.